In June of 2026, Microsoft stood in front of the world and said something extraordinary, that they had built a quantum chip 1,000 times better than anything they'd made before. And within hours, some of the sharpest physicists on the planet said the same thing they'd said the year before. We don't believe you. This is the story of a trillion-dollar company betting its future on a particle that might not even exist the way they say it does, and why the outcome of that bet could decide who controls the next era of computing. To understand why this moment matters, you have to go back further than most headlines bother to. Quantum computing has been the technology industry's most persistent promise for more than 3 decades. Since the 1980s, physicists have known that a computer built on the strange rules of quantum mechanics could, in theory, solve problems that would take a classical computer longer than the age of the universe. Drug discovery, materials science, cryptography, climate modeling, financial forecasting, all of it could be transformed if someone actually built a machine stable enough to harness that power. The problem was never the theory. The problem was always the hardware. Quantum bits, or qubits, are notoriously fragile. The tiniest vibration, the faintest stray magnetic field, even cosmic rays passing through the Earth's atmosphere can knock a qubit out of its delicate quantum state and destroy a calculation in progress. For decades, the entire field has been a race not just to build more qubits, but to build qubits that don't fall apart the moment you look at them. Most of the major players in quantum computing, Google, IBM, IonQ, Quantinuum, have approached this problem the same way. They build large numbers of imperfect physical qubits and then use software and clever engineering to stitch them together into more reliable logical qubits, essentially averaging out the errors. It works, but it's expensive and it requires enormous overhead. You might need 1,000 physical qubits just to get one trustworthy logical qubit. Microsoft looked at that approach and decided to bet on something almost nobody else was willing to try. Instead of fighting the fragility of qubits with brute force and error correction, what if you could build a qubit that was naturally physically resistant to error in the first place? That idea is called topological quantum computing, and it is the foundation of everything Microsoft has staked its quantum program on for the last 2 decades. The concept behind topological computing sounds like something out of theoretical physics fiction, because in many ways, it is. Instead of encoding information in the local state of a single particle, the way conventional qubits do, a topological qubit encodes information in a global property of a system, something that is spread out and protected by the very shape and structure of the material itself. Imagine trying to untie a knot in a rope versus trying to erase a mark drawn on a piece of paper. The mark can be smudged by the slightest touch. The knot's fundamental structure is far harder to disturb, even if you shake the rope around. That is roughly the intuition behind why topological qubits are theoretically so much more stable. They are protected not by shielding or correction, but by the physics of their own design. But there is a catch, and it's a massive one. To build a topological qubit this way, you need a particle that, for most of the 20th century, existed only on a chalkboard. It's called a Majorana fermion, named after the Italian physicist Ettore Majorana, who first predicted its existence in 1937 in a paper so strange that Majorana himself vanished mysteriously not long after publishing it, never to be found again. A Majorana particle is unusual because it is theorized to be its own antiparticle, a kind of physical impossibility that, if it could be coaxed into existing at the edge of certain exotic materials, could serve as the basis for an entirely new kind of qubit. For nearly 90 years, this was pure theory. Then, in the last decade, a handful of research teams around the world, Microsoft chief among them, began trying to actually create the conditions where something resembling a Majorana particle could emerge, not as a fundamental particle floating in space, but as what physicists call a quasi-particle, a collective behavior of electrons in a specially engineered material that acts, for all practical purposes, like a Majorana fermion. This is where Microsoft placed its enormous bet, and it did so publicly, repeatedly, and with a level of confidence that made much of the physics community nervous long before Majorana 2 ever existed. Back in 2018, Microsoft researchers published a paper claiming evidence of Majorana particles, only to retract it a year later after other scientists found flaws in the data analysis. It was an embarrassing moment for a company that had built its entire quantum strategy around this one physical mechanism, and it planted a seed of doubt that has never fully gone away. Then, in 2023, Microsoft came back with new results, publishing peer-reviewed research in a respected physics journal, claiming they had engineered devices that could induce and control what they called the topological phase of matter, bookended by Majorana zero modes. It was framed as historic, a milestone finally validating years of controversial work. In early 2025, Microsoft escalated further, publicly claiming to have created the world's first topological qubits, and unveiling a chip called Majorana 1, describing it as a breakthrough that could put a truly scalable quantum computer within reach in years rather than decades. The announcement generated enormous media attention, glowing coverage, and renewed excitement about Microsoft's quantum ambitions. But almost immediately, cracks began to show. Physicists outside the company pointed out that the core evidence Microsoft was using to claim the presence of genuine topological qubits relied on a specific measurement protocol, and that protocol itself had never been fully validated as proof of the underlying physics it claimed to demonstrate. A detailed analysis published in the journal Nature in the months that followed picked apart that protocol piece by piece, arguing that the test Microsoft relied on could potentially be satisfied by ordinary, non-topological effects, meaning the data didn't necessarily prove what Microsoft said it proved. It wasn't an accusation of fraud. It was something arguably more uncomfortable for a company that prizes scientific credibility, a suggestion that the entire evidentiary foundation of the announcement was, at best, ambiguous. That brings us to June of 2026 and the unveiling of Majorana 2, the moment that reignited this entire controversy and pulled it back into the spotlight. Microsoft's pitch this time was even bigger than before. The company announced that its new chip was 1,000 times more reliable than its predecessor, achieved in part by swapping the material used in its superconducting wires from aluminum to lead, a material more commonly associated with radiation shielding in hospitals and industrial facilities. According to Microsoft, this new lead-based material stack helps insulate the fragile quantum states inside the chip from the same kind of cosmic disturbances that plague every other approach to quantum computing. The company also touted faster operation speeds, with individual operations completed in roughly 1 microsecond, along with a dramatic reduction in the physical size of each qubit, now reportedly just 1/100th of a millimeter. Chetan Nayak, a technical fellow leading Microsoft's quantum program, described the improvement in stark terms during the announcement, stating plainly that compared to the year before, the new chip was 1,000 times better. Perhaps most striking of all was the roadmap Microsoft attached to this announcement. The company said it now expects to deliver a scalable, commercially useful quantum computer by 2029, cutting its previously stated timeline in half. That is an audacious claim in an industry where timelines have historically slipped again and again, where just a few more years has been the running joke among skeptics for over a decade. Microsoft didn't stop there either. The company revealed that its quantum team had used its own agentic artificial intelligence platform, branded Microsoft Discovery, to help accelerate the materials research behind Majorana 2, framing the announcement not just as a hardware milestone, but as a demonstration of how AI itself could speed up the pace of fundamental scientific discovery. It was a tidy narrative, tying together two of the most hyped technologies in the world, quantum computing and artificial intelligence, into a single triumphant press release. And for a few days, that narrative held. Then, the scientific community responded, and the response was not what Microsoft's public relations team had hoped for. Outside physicists who examined the underlying data and preprints attached to the Majorana 2 announcement raised the same fundamental objection that has followed Microsoft's quantum program for years. Extraordinary claims require extraordinary evidence, and what Microsoft was showing, critics argued, simply didn't meet that bar. Henry Legg, a physicist at the University of St. Andrews in Scotland, who has been one of the most vocal and technically detailed critics of Microsoft's Majorana research, pointed out that the data underlying the new claims appeared to come from only a small handful of measurement instances, taken on what looked like a single device. In science, and especially in a field as prone to false positives as topological quantum computing, that is a significant red flag. A single striking result on a single device could be a genuine breakthrough. It could also be a random artifact, a fluke of noise, or an experimental quirk that will never be reproduced again. Legg didn't mince words when describing the standard of evidence on display, suggesting that if a paper with this level of substantiation had come from any other laboratory, or from a graduate student rather than a division of one of the most powerful technology companies on Earth, it would likely never have made it through peer review at all. Sergei Frolov, another physicist who has closely tracked Microsoft's Majorana claims for years, added another layer of doubt by pointing to the company's publication history. He noted that Microsoft's previous major preprint on this subject had remained stuck, unpublished in any peer-reviewed journal for nearly a year, a delay that in the scientific world often signals that reviewers have serious, unresolved concerns about the validity of the underlying data or methodology. To Frolov and others watching closely, this pattern, bold public announcements paired with quiet, prolonged struggles to clear the peer review bar behind the scenes, has become almost a signature of Microsoft's quantum communication strategy. Announce first, in dramatic and confident language, to the press and the public. Let the harder, messier, more rigorous scientific vetting happen later, out of the spotlight, where the eventual caveats and unresolved doubts rarely generate anywhere near the same attention as the initial headline did. This is not a small, abstract, academic dispute. It sits at the intersection of enormous financial stakes, geopolitical competition, and the credibility of scientific institutions in an era when the line between genuine breakthrough and marketing spectacle has become increasingly blurred. Microsoft is not a scrappy startup that can afford to move fast and break things in its physics lab. It's one of the most valuable companies in the world, a company whose stock price, investor confidence, and competitive standing against rivals like Google, IBM, and Amazon are all, at least partially, tied to the perception that it is winning the race toward a truly transformative quantum computer. When a company of that size and influence puts its name behind a scientific claim, it doesn't just shape a research conversation among a few dozen specialized physicists. It shapes public perception, media coverage, government funding priorities, and billions of dollars in capital allocation decisions made by investors who, in most cases, have no ability whatsoever to independently evaluate whether the underlying physics actually holds up. And the government stakes here are just as real as the corporate ones. Quantum computing isn't just a commercial curiosity. It's viewed by governments around the world as a matter of national security and economic competitiveness. A sufficiently powerful quantum computer could, in theory, break many of the encryption systems that currently protect financial systems, communications networks, and classified government data. That threat, often referred to as the quantum apocalypse scenario for modern cryptography, has pushed governments to pour enormous resources into the race to develop or defend against quantum computing capability. The United States government alone has committed roughly $2 billion toward the goal of developing a scientifically validated, utility-scale quantum computing system by 2028, a timeline that, notably, sits right alongside Microsoft's own newly accelerated 2029 target. When a company's specific technical claims become entangled with national strategic timelines like that, the cost of being wrong, or worse, of overstating results in a way that misleads policymakers, becomes significantly higher than an ordinary scientific dispute. So where does that leave us, watching from the outside, trying to figure out who to believe? It's worth being fair to Microsoft here, because dismissing their work entirely would be its own kind of overreach. Topological quantum computing, if it can genuinely be made to work, offers real and significant theoretical advantages over the brute force error correction approaches favored by competitors. If Microsoft's engineers really have found a way to physically protect quantum information using the exotic properties of matter itself, rather than relying purely on massive redundancy and computational overhead, it could eventually mean smaller, faster, and more efficient quantum machines than anything else on the horizon. The scientific ambition behind this approach isn't fringe science or wishful thinking. It's grounded in decades of legitimate theoretical physics, and some very serious, well-respected researchers have spent their careers pursuing exactly this path, both inside Microsoft and in academic labs around the world. The fact that the road has been messy and littered with retractions, disputed measurements, and contested peer review doesn't automatically mean the destination is impossible. Difficult problems in physics are often solved slowly, with false starts, corrections, and years of frustrating ambiguity before a result finally becomes undeniable. But that same history is precisely why so many scientists are demanding a higher standard of proof before accepting Microsoft's latest claims at face value. This is a company that has, on multiple occasions, publicly announced breakthroughs using language like historic and first ever, only to have independent researchers later identify serious flaws or ambiguities in the underlying evidence. Trust in science is built cumulatively, and it can be eroded the same way. Each time a bold claim is followed by a walkback, a retraction, or a lingering, unresolved dispute over methodology, it becomes a little harder for the next announcement to be taken purely at face value, no matter how impressive the marketing materials look or how confidently company executives speak at press briefings. That's not cynicism. That's how the scientific method is supposed to function. Replication and independent verification aren't obstacles standing in the way of progress. They are the entire mechanism by which real progress gets separated from wishful thinking, statistical noise, or corporate incentive dressed up as discovery. It's also worth pointing out just how unusual Microsoft's public communication strategy has become compared to how most groundbreaking physics results are traditionally shared with the world. In an ordinary scientific process, a result of this magnitude, something that would represent the first confirmed observation of a nearly 90-year-old theoretical particle serving as the foundation for a new computing paradigm, would typically be submitted quietly to a top journal, subjected to rigorous, sometimes brutal peer review, and only announced publicly once that process had run its course and independent experts had signed off. Microsoft has largely inverted that order. The public announcements, the press briefings, the glossy blog posts featuring dramatic photography of chips lit in cool blue light tend to arrive first, generating massive media coverage almost immediately, while the more rigorous scientific scrutiny plays out slowly afterward, often stretching on for months or years, largely outside the public eye. By the time the more skeptical, technical rebuttals surface in places like Nature or in detailed physics preprints, the initial triumphant headlines have already reached millions of people, while the more cautious, critical follow-up reaches a comparative few. This pattern raises a broader question that extends well beyond Microsoft and well beyond quantum computing itself. In an age where technology announcements are increasingly treated as marketing events rather than scientific milestones, how should the public, investors, journalists, and policymakers evaluate claims of breakthrough progress in deeply technical fields that most people, understandably, don't have the specialized training to independently assess? It's not realistic to expect the average person, or even the average technology journalist, to parse the nuances of topological phase transitions or measurement-induced parity protocols. That expertise gap is exactly why the endorsement or the skepticism of the specialized scientific community matters so much. When physicists who have spent their entire careers studying these exact phenomena raise pointed, detailed technical objections, that skepticism deserves serious weight even when it runs directly against a wave of enthusiastic mainstream coverage celebrating the announcement as a historic leap forward. None of this means Microsoft is necessarily wrong about Majorana 2, and it would be just as much of a mistake to assume the company is engaged in outright deception as it would be to accept its claims uncritically. The far more likely reality, as is so often the case in cutting-edge experimental physics, sits somewhere in the uncomfortable middle. Microsoft's engineers may well be observing genuinely interesting and meaningful physical phenomena in their devices. The improvements in material science, the shift to lead-based superconductors, the dramatic reduction in qubit size, these are likely real, measurable engineering achievements in their own right. What remains genuinely, legitimately contested is whether those engineering improvements definitively prove the presence of true, robust, topologically protected qubits, the very specific and exotic physical phenomenon that underpins Microsoft's entire long-term quantum computing strategy, or whether the results, however impressive on the surface, are still consistent with more mundane explanations that don't require invoking Majorana physics at all. That distinction might sound like a minor technicality, but it is in reality the entire ballgame. Whether a scalable, commercially transformative quantum computer arrives by 2029, as Microsoft now claims, or whether that timeline slips by another 5 or 10 years, as skeptics increasingly suspect it will, depends almost entirely on whether this foundational physical mechanism is real, controllable, and reproducible at scale. If Microsoft is right, the payoff could be enormous. Not just for the company's balance sheet, but for entire fields of human knowledge that stand to be transformed by machines finally powerful enough to simulate complex molecules, optimize impossibly large logistics networks, or crack problems in materials science that have stumped researchers for generations. If Microsoft is wrong, or if the timeline proves far more optimistic than the underlying science can support, the consequences extend well beyond a single company's stock price. It risks feeding a broader, more corrosive skepticism toward quantum computing as a field, one that could make it harder for legitimate, well-supported research efforts, both inside Microsoft and at competing labs, to secure the funding and public trust they need to keep pushing forward. That is ultimately why so many people, scientists and non-scientists alike, are watching this unfold so closely right now. This isn't just a story about a chip, or a company's quarterly product roadmap, or even about quantum computing as a specific technology. It's a live, real-time case study in how modern science, corporate ambition, media incentives, and public trust collide with one another when the stakes are this high, and the underlying physics is this genuinely difficult to verify from the outside. Microsoft has placed one of the largest bets in the history of computing on the existence and controllability of a particle that, for most of the last century, existed only as an elegant idea on a theoretical physicist's chalkboard. Whether that bet pays off, whether Majorana 2 turns out to be remembered as the genuine turning point Microsoft insists it is, or as another chapter in a long pattern of overstated claims, eventually walked back by careful, patient science, is a question that no press release, no matter how confidently worded, can actually answer. Only time, replication, and the slow, demanding, unglamorous process of independent scientific verification can settle that question. And until that happens, the eyes of the physics world, the technology industry, and increasingly the general public remain fixed on Redmond, waiting to see whether this quantum leap is the real thing, or simply the latest, most expensive illusion of one.